Yeah, I can see your slide. Yes. Co-host. Should we just hold on? Yangu and who's your thing? Who's your? Just hold on. Where? Well, Yangu is one, right, in the panel,
Yes.
and Gayatri is your. Is Gayatri your?
No, she changed in my
Okay,
CA1. She was my. She
okay.
told it's not possible to be there.
So Leonard is in this. Leonard, no?
Leonard is my co-supervisor.
Okay, yes, okay. Okay, I'll send to him. I think they must be in the other room. Yeah, I've sent. Is shown here now.
Hi, Mohsen.
Hi.
Hi, how are you?
Thank you.
Hi, everyone.
Hi,
Shirley.
hi, Leonard.
Hi, Shirley.
Yeah, I provided. There were two links. I'm not so. Did you go to the other link or?
Yeah, the three of us were there.
Yes.
Yeah, we just
Yeah.
yeah.
I don't know how it happened, but yeah. Just hold on.
I think everybody's here. Yeah.
Yeah, okay. Just hold on. Let me take Okay, now. Okay, sorry. There was some miscommunication with the link. So I think all the panels here, right? Shows here, Young was here. Okay. Okay, you can share your screen, Mohsen. So, good afternoon, everyone. Welcome to this CA3 for Mohsen Askari. He will be presenting on the selective lithium recovery from brines using advanced capacitive deionization. Principal supervisors are Professor Hok Kyung Sean and co-supervised by Associate Professor Leonard Tihing. And we have myself will be the chairing this CA3, and I have my fellow assessor, Dr. Yang Wu Chu. So most of you have 30 minutes for your presentation, and then we will have a question and answer and by the panels, followed by your supervisor, and then from the audience. So yeah, so just the first thing is that this is being recorded, so you should be okay, right, for recording, so that you can in a contest for the best presentation award.
Yeah.
Okay. Thank you. The floor is yours, Mohsen. Yeah.
Can I start?
Yes, please.
Good afternoon, everyone. Thank you for attending my candidature assessment stage 3. Today, I present my research on selective lithium recovery from brine using advanced capacitive deionisation CDI conducted under the supervision of Professor Ho Kyung Shan and Associate Professor Leonard Tijing. First, I introduce the introduction and research design, then general experiment technique will present, then objective 1, 2, 3, and after that, conclusion and recommendation will be presented. Lithium demand has increased. The lithium demand has increased production in recent years, mostly for battery manufacturing that consume 87% of the lithium, and the market research shows there is a high demand of lithium-ion batteries in next years, and it's expected to continue. But the main question is, how do we meet growing energy demand while reducing the environmental impact? However, there are resources are abundant for the lithium extraction. Production is concentrated in some regions, and there are the harmful for the supply chain. One of the good sources are brine, has the large reservoir, growing production capacity and potential for more sustainable extraction. In contrast to conventional brine extraction that relies on evaporation ponds, direct lithium extraction DLE is based on the engineered separation. It can improve the recovery efficiency to 70 to 90%, decreasing the processing time from months to years to the hours to days, decreasing the land footprint and improving the water consumption. It has large resources, expanding production, and strong potential for sustainable extraction. Our patent analysis on direct lithium extraction on brine shows from 2010, the attention has been increased more than 20 times. And among all the technologies, electrochemical technologies are emerging, has the diffusion speed in comparison with other technologies. Among the electrochemical technologies, CDI has been considered for some main reasons. It has low energy consumption, modular and scalable, regenerable and reusable process, and selective recovery potential because it can integrate with advanced electrode and membrane. But the research gap is answering this question. What prevents efficient lithium recovery from real brine with CDI? Up to now, most of the abundant lithium resources are in the low lithium concentration and high magnesium to lithium ratio. For CDI, the key barrier is material limitations, selective limitation, and stability and system limitation. This shape three main questions: how can lithium absorption capacity and connectivity be improved? How can selectivity lithium recovery over magnesium be enhanced? And how can recovery selectivity, purity, and stability be optimized simultaneously? This shapes three main objectives of this project. I will present them. The general experiment techniques are used for preparing the composite and electrode based on the casting and deep coating, and the 3-electrode cell and CDI cell that was used for electrochemical evaluation and performance evaluation framework of the CDI based lithium recovery in different categories has used to evaluate the process. For the first objective, we focused on using the Maxing-based electrode. As I told, the main challenge is the limitation of the capacitance of the materials. Maxing, in comparison with the conventional active carbon, has a high potential for adsorption capacity. It's a two-layer nanomaterials that has layer structures, but the main challenge is mitigates the restacking the layers. There are some strategy to mitigate this restacking. One of the best methodology is using the composite. Because of that, we use the Maxing SNO2 to mitigate the restacking and enhance lithium adsorption capacity and performance. The Maxing SNO2 composite and electrode were prepared, and the HCDI cell of the Maxing SNO2 AC cell was assembled. This SEM shows how SNO2 being anchored on top of the layer and between the layer and help the restacking the lamellar structure of the Maxing, and FTIR, XRD, and XPS shows the successful preparation of this composite. The EIS shows using the SNO2, the conductivity will increase and lithium ion accessibility and pathway for the lithium ion transport will be improved. This run in the CDI test for adsorption study in single ion adsorption of the sodium, potassium, and lithium, and the ternary of these ions. In the ternary ions, we saw the lithium preferential is increased, while in the single ion, we saw potassium and sodium has the high preferential to lithium. And in selectivity, the lithium was a higher selectivity than potassium and sodium in a ternary solution. The reason of the this mechanism was studied based on the adsorption rate and desorption rate of these three ions. As can we see in this table, the adsorption and desorption kinetics was with potassium, sodium, and lithium. Sodium and potassium has fast surface adsorption. They have fast adsorption and fast desorption at the same time. Why the lithium has a slower adsorption and slower desorption, and it shows the intercalation with Maxing layer and storage at SNO2 site. So slow adsorption and desorption kinetic of the lithium help to have the higher retention through the intercalation and so to capacitive storage of the electrode. We run it for the 20 cycles, and after that, we saw the salt adsorption capacity is 103 milligram per gram. Is the highest amount of the lithium adsorption reported as the comparative performance in this table. And after 20 cycle, 82% of the capacity was retained. It shows it has the high capacity of the lithium adsorption, and the stability is acceptable and it's good. Conclusion of this chapter was the composite engineering effectively mitigated the Maxing restacking, creating a more accessible electrode architecture, and the heterostructure integrated conductivity, ion accessibility, and active storage site within a single platform. The conductive network promoted rapid ion transport and adsorption kinetic, and the electrode achieved high capacity lithium recovery with 82% capacity retention after 20 cycles. But there are some remaining limitations. Limited lithium selectivity over competing ions, higher uptake of the sodium and potassium indicate insufficient ion discriminations, and performance require validation under realistic higher magnesium to lithium brine conditions. Based on these limitations, the next challenge is achieving the high selectivity of the lithium recovery through enhanced lithium to magnesium separation using a lithium ion sieve strategy. That is the target of the next objective. We selected the lithium titanium oxide, LTO, and since it has the high lithium selectivity as a lithium ion sieve material, excellent structural stability and good regenerability and durability, while it suffers from the low electrical conductivity, slow lithium absorption kinetic and lithium active site accessibility and other weak points. So the hypothesis was the Maxine engineered HTO can combine the selectivity of the lithium ion sieve with the rapid charge transfer and ion transfer required for efficient lithium recovery. Based on this, we first compared the layered and spinal structure of the HTO based on the electrochemical test. The layered HTO shows higher capacitance and large charge storage response, while spinal HTO show the lower the RCT and faster lithium insertion and extraction kinetics in EIS. Therefore, the spinel HTO is more suitable for rapid and reversible lithium recovery and selected for our next experiment. So we have the HTO Maxine as a composite with prepared based on this procedure, and we have expected to have the selectivity and high lithium rate with this composite. The SEM image shows, like the previous chapter, the HTO are anchored on the top of the Maxine sheets and between the layers. And the interconnected nanoporous architecture has been formed that suppressed the Maxine restacking and created some open ion transport channel and hetero interfaces. The characteristic of the TIO vibration of the HTO in FTR analysis were returned after hybridizations, broadening of the 500 to 800 region indicate the interfacial interaction between H2 and Maxine, and preservation of the TiO6 octahedral framework confirmed the structural stability of the STO. And for XRD analysis, the Maxine reflection on 9-degree confirmed rotation of the layer Maxine structure, and H2 spinel reflection remain visible, confirming preserving of the lithium ion sieve framework after making the electrode. And based on the cyclic volummetric test, we optimized the amount of the Maxine, because when Maxine increased more than 20%, the CV area will decrease. It shows the conductivity should be optimized, and 20% of the Maxine has the highest current response and achieve the optimal balance between the conductivity and active H2 site. So we selected the HTO and Maxine 80 to 20% of each as a composite for our next experiment. First, we studied the effect of operational parameter of the CDI, feed concentration, pH, and applied voltage presented in my CA2 in details. The key finding here was the applied voltage. In my previous study on Maxine, I found increasing the Maxine increased the absorption capacity, but here there is an optimum, and it should be a maximum 1 voltage to have the highest absorption capacity and absorption rate. We compared the HTO and HTO Maxine electrode, and it shows that absorption will be improved 60%, and absorption efficiency means absorption rate, absorption capacity improved 60%, absorption efficiency improved 64%, and it shows the synergistic effect of the HTO and Maxine, while HTO provide the selective lithium ion sieve sites and Maxine enhanced conductivity and ion transport. In binary and ternary solution of the lithium, sodium, and magnesium, each 5 millimolar it tested, and the result shows the preferential of the lithium other the ions in binary and more importantly in ternary solutions, and the high selectivity of lithium over these two ions demonstrated the selective lithium recovery across the complete absorption and desorption cycle. We used here to formula extraction selectivity and relative selectivity. Relative selectivity is just for adsorption, and extraction selectivity is in adsorption and desorption cycles. Then we use the simulated desalination brine feed solutions and run the electrode for 8 cycles. It shows the high lithium to sodium selectivity and lithium to potassium selectivity in cycle 1, and lithium selectivity remain more than 100 after 8 cycle, and steady state performance achieved after cycle 6. It decreased the stability and then it stabilized. Why the lithium adsorption increased in the right graph from 5% to 97% in adsorption, and enhanced electrode penetration and charge transfer help to have the highest selectivity, and SEM shows the structural stability is acceptable after this test. As a mechanistic of the selective lithium recovery insight, we can say in initial stage, incomplete electrolyte wetting limit active site accessibility, and restricted ion transport lower initial lithium adsorption, and competitive ion adsorption reduce apparent selectivity. Maybe because of that, the stability, the amount of the selectivity after first cycle decrease, but after in next cycles, the progressive electrolyte penetration activates the previously inaccessible H2 sites and improve charge transfer and reduce diffusion resist and enhance the lithium transport, and lithium adsorption increase while selectivity is stabilized after repeated cycling in 7-8 cycles. Key conclusion here is spinel HTO provided better electrochemical kinetic for this target compared with the layered HTO. Maxine created the conductive and ion accessible network while suppressing the restacking by HTO. Higher lithium adsorption capacity and faster kinetic than the pristine HTO was observed, and a strong lithium selectivity maintained in the binary, ternary, and simulated desalination brine feed solutions. So HTO Maxine successfully combines the lithium selectivity of the spinel HTO with the fast charge transport of Maxine, enabling efficient and selective lithium recovery from complex brine. The remaining limitation are selectivity decrease gradually during the prolonged cycling is one of the main challenges in CDI systems, and competitive adsorption by sodium and magnesium and calcium is not fully eliminated. It's affected in next cycle on the lithium selectivity, and the long-term stability remain unverified. Based on this idea, we went to objective 3 to look at again the position of the CDI in this process of the DLE. The CDI is the intermediate process that can extract the lithium and provide the lithium enrichment process. Based on our literature review, we found the CDI effectiveness is the ability to convert this low quality brine, means low lithium concentration and high magnesium ratio, into a lithium rich stream with high recovery, purity, selectivity, and stability. So the hypothesis in this chapter is investigate whether a membrane electrode architecture can overcome these trade-offs and enable lithium enrichment from low quality salt lake brines. So we worked on the selectivity, purity, recovery, and stability to make them balance. For this target, the design strategy was producing a novel membrane electrode. First, the active carbon electrode prepared and cross-linked, and based on the glutaraldehyde, here PVA used as a binder. Then the HTO Maxine developed in the previous chapter put in the PVA matrix to provide the membrane on top of that electrode, and based on the hydrogel casting and freeze thawed and peg removed and cross-linking, interconnected porous structure was formed. After that, for using in MCDI, we put the cation exchange membrane laminated on top of these layers, and with layer by layer with polyethylene imide and polystyrene sulfonate, put the layer by layer in which the outer layer is the positive layer. So we have these kind of structures, active carbon based on the PVA, H2O max in PVA. These have the synergistic because both of them are PVA have a good lamination, cation exchange membrane, and the LBL layer that the outer surface has the positive charge. The SEM shows the AC active carbon electrode has a porous carbon framework for rapid ion transport, and H2O maxing membrane has a conductive, can be conductive hydrogel with uniformly distribute the lithium ion site and maxine, and interconnected porous structures provided and expected to have improved the electrolyte accessibility and improve performance. For experimental framework in stage 1, we optimized it with the binary of the lithium to magnesium with the conventional batch CDI experiments. And in stage 2, we used the synthetic salt-like brine as presented in this table with the multi-enrichment process. It means in every cycles we used a new feed, but we use the same desorption solutions and try to enrich the lithium in the desorption phase and collected the lithium to understand how we can balance the selectivity and purity of the lithium at the end. In first stage, binary of the lithium magnesium, each of them 5 millimolar in binary solution was tested, and the number of the LBL was optimized. The result shows the 24 layer of the positive and negative layer can has the highest efficient results, and also the effluent concentration shows the lithium decreased from 5 to 3.5 millimolar, while magnesium remained nearly unchanged. That shows magnesium is not penetrated into this layer. For using the next experiments, we use the recovery fraction, lithium capture performance, extraction selectivity, and recovery quality metrics. We try to balance these parameters and trade off them. The result shows the progressive lithium enrichment over 6 cycles is possible. Lithium recovery increased from 6.3% to 70%, while the sodium and magnesium recovery remained low, less than 3 and 2%, and a stable lithium capture performance in which the lithium removal efficiency remained 36 to 61%, and lithium capture established at about 22 milligram per cycle after cycle 4. And the selectivity improved, and at the end, recovery against the purity trade-off shows the continued cycle increased lithium recovery, but a slight impurity accumulation appeared after the cycle 5. As a result, cycle 5 provided the best balance between recovery, purity, and selectivity, in which it enriched the lithium from 294.5 milligram to about 690 milligram per liter, shows about 2.3 lithium enrichment. So 5 cycle of this MCDI can have a good balance between the enrichment, purity, and selectivity. And the result is a one-step fast MCDI process in 5 cycles that has 2 stage. In first stage, based on the Dunan exclusion, suppress the magnesium transport based on the cation exchange membrane that regulate the cation flux and enrich the lithium transfer. And on the other hand, in stage 2, the H2O max in hydrogel has a fast and high selectivity of the lithium adsorption, in which the hydrogen facilitates rapid ion transport and active site accessibility. The outcome is simultaneous magnesium rejection, lithium enrichment, and selective lithium recovery. As a conclusion, LBL modified H2O Maxine membrane electrode achieves selective lithium recovery for high magnesium lithium brine, multi-stage ion discrimination, combined transport selectivity and lithium ion sieve storage, lithium recovery, purity, selectivity, and enrichment. Enrichment exhibited a strong depends, and cycle 5 provided the optimal balance between recovery, purity, selectivity, and process efficiency. And the one-step MCDI enrichment reduced the need for additional washing and purification stage, and it can be a cost-effective method as a fast and high efficient process for lithium enrichment. Final conclusion and recommendation. The key conclusion is Maxine-based composite engineering enhanced lithium recovery capacity, transport kinetic, and cycling stability. Integrating spinel H2O with Maxine successfully combined high lithium selectivity with rapid electrochemical kinetic. Advanced CDI performance is governed by balancing recovery, purity, selectivity, and stability rather than maximizing selectivity alone that is usually reported. The integrated H2O Maxine CDI platform enable one-step lithium enrichment for high magnesium to lithium brine. An intelligent membrane electrode integration provides a promising pathway for practical lithium recovery from low-quality brine. For future recommendation, optimization, the regeneration, and lithium desorption strategies are suggested, because in last experiment, I see the changing the desorption and washing increasingly increase the dramatically increase the efficiency of the process, and further advance on the membrane engineering is suggested, and integrated CDI enrichment with downstream lithium production using the post-treatment after CDI as a two-stage process can be a further recommendation for future research. This is a list of publications, review papers, and some technical papers around CDI, and 3 manuscripts in preparation, and I hope to submit them before my thesis submission. And at the end, I want to sincerely thank my supervisor, Professor Ho-Kyung Shan, and Associate Professor Leonard Teaching for their guidance, support, and valuable advice throughout this research. And also thanks all my collaborators and colleagues, Dr. Andrea Miranda, Hamday, Daisharania, Gabriel Jake, Said, and all colleagues, lab mates, and friends for their assistance, collaboration, and support. And thanks for ARC Industrial Transformation Research Hub for Nutrient in a Circular Economy, NICE Hub, for supporting this research, and UTS for financial support, the scholarship of this research. Thank you for listening, and I'm happy to answer your question.